Hello, everyone, and welcome to week 19 of Qubit by Qubit's Intro to Quantum Computing. Today, we're going to be talking about quantum key distribution. So kind of following up from last week where we started off with our first, as I called it, sort of fully fledged quantum algorithm. Today, we're going to be looking at a second one, quantum key distribution, which is a little bit longer, a little bit more involved, but hopefully with last week under your belt, this won't be too much of a stretch going forward. I will just make a quick note here right off the bat. I wasn't able to get my headphones working this morning for some reason, so I hope that the sound quality is still okay, but my apologies if it sounds weird compared to normal. Quick program for today. We'll start off with our Canvas attendance quiz as always. Then we will do the pre-lab Zoom feedback. We do have a couple of questions from last week, which I guess are not directly related to superdense coding, but are sort of generic quantum computing questions that certainly come up when we talk about superdense coding. So we took these from Piazza and a couple of other places, and we'll be giving sort of quick answers to them here. Hopefully that helps alleviate some confusion. And then we'll dive into the main lab content. So the lab content for today is going to be maybe about a third on slides. So just me describing quantum key distribution from a theoretical perspective. We'll look at some of the, I guess, new features and, well, not new, but we'll do a review of features in Python to make sure we all know what's going on when we eventually look at the code. And then we will move over to the IBM Quantum Experience and look at the Jupyter Notebook for this week and actually code out some of the steps of QKD, as it's called. Okay, so let's go ahead and launch the Canvas attendance quiz. So as always, lab number is 1. The quiz password this week is 7048. The question we're asking is, on a scale of 1 to 5, how comfortable are you with creating and executing circuits using Qiskit? So Qiskit, and Python for that matter, is probably new for a lot of people here. We've been using it for a couple of weeks now, and as we are getting into more complicated circuits with Qiskit, such as superdense coding or quantum key distribution, we just wanted to get an idea of how everybody is managing, how you're finding this new tool. As always, the quiz is not graded, but please do fill it out for your lab attendance. If you have any issues with the Canvas attendance quiz, please feel free to throw those in the chat. Or if you just have any other random comments, I opened up the chat. And in the meantime, let's do the pre-lab Zoom feedback. How is everyone feeling this week with the content generally? Like, were there any topics that, I guess everything was QKD, but were there any parts of QKD that in particular seemed confusing to anybody? Okay, so far so good. All right, let me go ahead and, well, actually, why don't I go over the agenda? Oh no, we have our questions. Okay, so I'm gonna end the poll here and then I'll share the results with everyone so you can see where people are at. There we go, so lots of people in the 3 or 4 category. So hopefully we can try and bump that up as we go through today's lab. So before we get into QKD, these are the few questions from last week that I wanted to go over. Now, there's 3 questions here. Each of them is pretty much a binary question, as in yes or no. But each of them is not exactly super clear, right? And again, these were ones that just came up, questions that sort of came up on Piazza. The first question is entanglement superposition, or more generally, we've been throwing around these 2 terms, entanglement and superposition, and we haven't exactly formally defined them. So what is the connection between these 2 terms? Does one imply the other? Are they the same thing? That kind of thing. The simple answer to this is that they are not the same thing. And one misconception that some people have is that superposition refers to a state of a single qubit, right? So I could have a single qubit in a superposition, which is true. But entanglement refers to multiple qubit systems, right? So you can't have a single qubit being entangled with itself. That's not a thing. Entanglement can only exist between two 2 or more qubits. Superposition can exist between 1 or more qubits as well. I just saw somebody in the chat saying there's no sound. Okay. Thank you to those of you who confirmed. Yeah, so entanglement and superposition. It is fair to say, and it's correct to say, that entanglement only exists between 2 or more qubits, while superposition can exist between 1 or more qubits. But that's not to say you can't have a 2-qubit superposition, right? I could totally have a 2-qubit superposition. The Bell states are an example of that, right? So this 1 over root 2 ket 0, 0 plus ket 1, 1, that's a superposition. And the easiest way to tell that it's a superposition is just whether your quantum state has any additions in it. It's really that simple, right? So if when you write it down, you're writing it as basis state plus basis state plus basis state, et cetera, then it's a superposition. And that is pretty much the definition. Now, this state that I wrote down, this Bell state, it also happens to be entangled, right? And we talked a little bit more about what it meant for qubits to be entangled in a previous lab. It's not quite as straightforward as looking for a plus sign, but I won't go more into that right now because we did do it earlier. So yeah, entanglement and superposition, they are different. I guess they are kind of related in that entanglement always requires superposition, but you can have superposition states that are not entangled. You can have 3-qubit superpositions. All of those are possible. So hopefully that helps clear that one up. Second question, can more than 2 qubits be entangled? So we've seen in the past couple of weeks the Bell states are an example of entangled states. We've mentioned that a couple of times. That's an example of a 2-qubit entangled state. Is it possible to have 3, 4, 5-qubit entangled states? The answer to this is yes. You can entangle as many qubits as you want. You could have 10 qubits all being entangled with each other. Now, sometimes this misconception about only 2 qubits being able to be entangled with each other, sometimes that comes from how we do this in the lab, because oftentimes when you construct, for example, a 3-qubit entangled state, the way you do it is by first entangling qubits 0 and 1, and then you entangle, for example, qubits 1 and 2 with each other. So usually to build up these larger entanglements, you do them in pairs, but the ultimate entangled state is indeed an entanglement between arbitrarily many qubits. So I guess this one, can more than 2 qubits be entangled? Yes. That's the simple answer. And then the little bit more detail is that often when you prepare these many qubit entangled states, you prepare them by entangling pairs. Third question, can we use entangled states to send information faster than the speed of light? So this one came up a couple of times on Piazza. I know there is actually one student question that came up with a pretty elaborate scheme for how to do this in theory. We're going to look at that and see if we can find what's wrong with it. But in general, this has been proven to be impossible. So no, even with entanglement, even with quantum teleportation, superdense coding, whatever you want to use, you cannot send information faster than the speed of light. Now, what often leads to this confusion is that entanglement, right? If you have 2 states that are entangled, modifying one of them has an immediate effect on the other one. So if I measure qubit 0 and it's entangled with qubit 1, then we learned that qubit 1 will instantaneously, i.e. faster than the speed of light, modify itself, right? Because they're entangled. The problem with that is, though, is that even though that difference we think happens instantaneously with entanglement, you can't glean any important information from it. So the key here is that it's impossible to send information faster than the speed of light. In other words, if I wanted to send you a bit string using entangled states somehow, we could use quantum teleportation to do that. But if you remember from last week, quantum teleportation still requires you to send some classical information. So you would have to wait for that classical information to travel at the speed of light before you can do anything with the result of your entanglement measurement. Now, the proof for this and why this works is beyond what I know. I would love to be able to go over it, but I don't know it. I don't know, I guess, a nice, simple way of seeing how this can be proven. But it has been proven that quantum mechanics does not justify in any way faster than light information transmission. Okay, so any questions on this? So somebody says, I usually get confused when I see things like the 1 over root 2. Is there any material that I may review that can help visually? So the 1 over root 2 comes from the world of linear algebra. And the reason for it is because our qubit states have to be normalized. I will try and dig up what lecture or what lab, sorry, we went over normalization in. But that would be my recommendation, is to review normalization. Okay, great. Glad to hear the audio problems are resolved by rejoining the meeting. So let's move on to this week's actual content then. As I said, this week is all about QKD. Now, before we jump into the actual QKD protocol, right, how it works, as I said, we're going to review some important coding concepts. So this should be actually fairly quick because in one way or another, we have technically seen all of these things before. Some of them have been in optional content though. So I'm just going to go over everything now to make sure we're all on the same page about the coding concepts you need to understand QKD. Then once we've done all this, by the way is on the slides. So I will do that on the slides here. After we've covered all that Python review, then we're going to hop over to the IBM Quantum Experience and write the circuits in Python using Qiskit for QKD. The final piece, the optional content for today, which as a reminder, I always go over, although it will go past our 1 hour limit, is going to be sort of the second half of the QKD algorithm. So I'll talk more about this when we get to the notebook, but essentially I will need both the required and the optional time to cover the whole algorithm, but that's okay. All you need to be here for is the first half. The second half is similar and honestly, I think easier than the first half. So we're going to go over the tough part here. And then in the optional content, I'll sort of finish everything off for completion, but you shouldn't be too bad off if you only are here for the required stuff. Okay, so let's hop into our Python review. Oh, sorry, I had a minor technical glitch. There we go. Okay, so the first thing we'll look at is generating random bits in Python. So one of the steps in QKD is we're going to have to generate what we call random bit strings for a couple of different use cases. Now, a bit string is just literally a sequence of ones and zeros, right? So this could be a bit string, totally valid. We're asking here to generate a random bit string, right? So we just want to be able to call some function in Python to get ourselves a random bit. So in this case, it'll either give us a 0 or a 1 with 50-50 probability. How do you do that in Python? Well, oops. Should read this part first. Yeah, sorry about that. This slide is just sort of motivating a little bit why we want to generate random bits, but I already kind of talked about it. So Alice and Bob need to generate random bits to perform QKD. I'm going to kind of skip over these because I think we'll talk about them more when we get to the notebook. And then the question now is, how do we generate random bits in Python? The answer to this is this function getRandBits. Okay, so that just stands for get random bits. It comes from the random library, as you might expect. Everything to do with randomness in Python comes from this library. So we are going to have to import that library as well, right? It works just the same way as Qiskit. It's like downloading a new app onto your phone. Now we want an app that deals with random numbers. And so we're going to have to import random. And then we use this getRandBits function. Now in our lab, we're always going to put 1 here. We're always just going to generate 1 random bit at a time. But if you wanted to, you could plug in any number into this function, and it would give you n random bits in general. So what does this look like? Well, first of all, we need to import the function. So this should look fairly similar to what we've seen with Qiskit before, right? In Qiskit, we often had, from Qiskit Then we would do import air, quantum circuit, all this kind of thing, right? So it's the exact same idea. We are importing certain objects, functions, from this library random. Then to actually generate our random bits, we're going to use that function getRandBits that I mentioned. So as I said, we'll always be using getRandBits1. The 1 here just means that you're generating one random bit at a time. So this function is going to give you 0 with 50% probability, or 1 with 50% probability. Okay. Next up, appending strings. Another thing that we're going to have to do is build strings iteratively. As a reminder, in Python, a string is just a sequence of characters, right? So I think we have a bullet here for that. Now, I could start off with an empty string. And all I mean when I say we're building a string iteratively is that we're sort of adding on to it one at a time. So maybe I start with an empty string, and then I'm going to add on an A, and then I'll add on a B, or oops, add on a B. So we'd go to A, B, and then I would add on a C. Something like this, right? So we know how to declare a string in Python, right? We could call it, my var equals, and then you do a string character, and you could say hello, right? That's how you create a string. But now if I wanted to add on to that string, how do I do it? That's what this slide is going to answer. So that process of sort of adding on to a string is called appending in programming. So in order to append strings, we actually just use the plus operator. So again, I'll go over why we use this in QKD when we get to the notebook. But like I said, to do this, we just need to use plus. So in this example, Alice would have some bit string. So for example, she might have 0, 1, 0, 0, 1. And now we are going to essentially overwrite this and set it equal to Alice's bit string, which is 0, 1, 0, 0, 1, plus, now what this is doing here is it's getting one random bit, right? Either a 0 or a 1, then it's converting it to a string. That's what this little stir does. So let's say that getRandBits spits out a 0, then we'll have a 0 string here. And this string plus string notation in Python, that's going to lead to an output string 0, 1, 0, 0, 1, and then 0. Right? So we've literally just sort of glued that extra bit onto the end. That's all we're doing here. So after this line is executed, Alice's bit string will be equal to this, 0, 1, 0, 0, 1, 0. Now, there is an alternative notation for writing this. We can simply write it as Alice bit string plus equals stir get random bits. Now, these two statements are actually exactly the same. So this little plus equals notation in Python is just a shorthand for this upper statement here. So it's basically saying, take Alice's bit string and then add on, or again, sort of glue to the side, one of these random bits. Let me just pause. I saw quite a few questions going. Yeah, so I will review so somebody said, I haven't reviewed the lecture material from Sunday. Could you clarify and review what the direction of the arrows of the bases represent? Yes, absolutely. And then somebody says, the original Alice bit string 01001 was just an arbitrary number picked by Alice and not a random function. Yeah, good question. So in my example here, I just came up with that off the top of my head. I just picked some random string to demonstrate what this does. In the actual QKD protocol, we're going to be randomly generating that string one bit at a time. So somebody says, this doesn't always give the same length string. Interesting. Let me see. So rand key equals bin random.getRandBits 50. I'm not sure. Maybe when we get over to the Jupyter notebook, I'll try actually running that code and see if we can figure out what's going on. Oh yeah, this is a good question. How does getRandBit actually produce random bits? Yeah, so that is something, I'll just give you a name that you can look up if you're interested. It's called pseudo-random numbers. And so there are certain algorithms that generate pseudo-random numbers. And the reason that they are called pseudo-random is because they aren't truly random, right? Truly random would mean that you, I don't know, like look to the stars and use the brightness of some star to determine your random number. Here, we're just using something on our computer. So essentially, our computer is simulating randomness. Kind of like when we used the simulator in the IBM Quantum experience, we saw how it sort of flipped a coin 1,000 times to simulate randomness. Kind of a similar idea here. It's not true randomness, but it is close enough to random for our purposes. Okay, so then somebody asks, why not use quantum states to generate random bits? You could, right? So that is a valid way of generating random numbers, is you could prepare, here's just one example, there's many ways to do this though. You could prepare the state ket plus and then do a Z measurement. And we should know that a Z measurement of ket plus leads to ket 0 50% of the time and ket 1 50% of the time. It's totally valid, and this is a truly random, way to generate ones and zeros. The issue is that, when I'm sitting here on my laptop running get rand bits in the Python notebook, I don't have access to a quantum computer, and it's kind of overkill to create a qubit and run a quantum computer just to generate a random number. But you're right that you can totally do this. It's totally valid. It's just kind of overkill given how expensive quantum computers are. Okay, let's go on to the next Python concept then. We've got 2 of them left. This one is appending to lists. So as a reminder, a string is a thing in Python that's essentially just a sequence of characters. A list is sort of like a generalization of that, right? A list lets you store a sequence of anything. It could be a sequence of numbers, a sequence of letters. It could be, I don't know, a sequence of qubits, right? And actually that's how we're going to use it in today's lab. We're going to have to store a list of qubits somehow. And we're going to use a Python list for that. Again, I'll talk in more detail when we go to the notebook about how this works in step 3. But the question then is, how do we append to a list? So it works pretty much the same way as, the intuition is the same as what we just saw. The syntax in Python is a little bit different. For lists, we're going to use the append function. So instead of using that sort of plus equals business, we're going to do list.append. Now, just to map out exactly what this would do, suppose up here, encoded qubits is a list. So I'll do it with square brackets. And maybe we have, ket 0, ket minus, ket plus as our list so far. And then we're going to append QC, and suppose QC is another ket 0. Then after this line, we're going to get encoded qubits equals ket 0, ket minus, ket plus, so the same that was in there before, but now it's going to have our additional new element on the end. Okay, so both of these, appending to strings, appending to lists, it keeps what you already had, and it just tacks on something new at the end. Final concept is Python functions. So this one I'm going to go over pretty quickly because we literally saw this exact thing last week. We probably should have done a slide for it last week before we put it in the notebook, but we're doing a slide for it now. Hopefully that's okay. So the most common use of functions is to, as it says here, create a piece of code that you can run as many times as you want. And in our case, we are going to have some sections of our algorithm that we want to run multiple times. This is how we saw before, how you define a function in Python. You use the def keyword. So you define a function, you give it a name, such as encode, and then you can pass in a certain number of arguments to that function. So in quantum key distribution, I will expand a little bit on why we want to do this. We want to be able to create long keys, right? So I will also explain exactly what a key is and all that kind of stuff when we get to the notebook. but we want to create these sort of longer keys. And each bit of the key corresponds to one qubit that Alice has to send. So we could go ahead and sort of manually produce every single qubit, or we can just define a function to do it for us. And so that's what we're going to do. Because these keys can get really long, we're just going to use functions that generate each bit of the key for us, and then we can run it in a loop or something to give ourselves 500 bits in the key. So last week we started modifying quantum circuits inside functions. Here's one example that we saw, right? We had this create bell pair function. And the only interesting thing about it really was that it took the quantum circuit, QC, as an argument. And then once we had that argument inside our code, we could then apply an H gate to it or apply a CX gate. Now, previously we have talked about the quantum stack. Well, in this case, we've taken a step sort of up in the quantum stack, right? Now, instead of directly modifying the circuit every single time, we're going to create functions that modify the circuit that are ultimately going to be run on a simulator or a quantum computer. So this is convenient for us. Functions are not something that's, I guess, strictly required in Python or programming in general. It's just a convenience, right? It allows us to bundle up our code and essentially copy paste it in multiple different locations. As I just sort of explained, the general idea is that we have functions in Python that create quantum circuits that are then going to run on a simulator or on an actual quantum computer. So we're going to have a lot more of that kind of stuff going on today. That brings me to the end of the Python review. So next up is going to be jumping over to the IBM quantum experience. I'm just going to take a quick look at the questions, though, before we move on. Oh, can I show my screen on appending to a list again? Sure. Actually, I should have just done this. Appending to a list. I think it was this. There you go. Oh, interesting. So somebody says that the Qiskit book uses a different notation for generating these random bits. That's okay. There's definitely a lot of different ways to do this. We're going to use the getRandBits function, but don't be too surprised if you see other variations out there. Okay, cool. So I think, why don't we hop over to the IBM quantum experience? I will go over a little bit more on QKD, and then we're going to code the first half of it. Just give me 1 second to switch over. Okay, I think this is the correct screen. All right, so hopefully everyone can see my Jupyter notebook here. I will zoom it in. B3. How does this look for everyone? Does that seem okay? Cool, thank you. All right, so let's go into a quick overview of the Jupyter Notebook part of today's lab. I guess, yeah, so in the introduction, I will talk a little bit more about QKD, how it works, what it's aiming to accomplish mainly, because I think it's important to try and sort of contextualize what's going on. Then, just like last week, we're essentially going to go through the steps of the protocol, right? So we're going to have one section for each step. We'll describe what it is, and then we'll also show how to code it. And hopefully that's a good sort of organized way of outlining how this algorithm works. That's actually it for this lab. We're just going to spend all of the rest of today on QKD. Then I'll go over key takeaways and further readings, but you'll notice here that steps 5, 6, and 7 are actually in the optional content. As I said before, they are optional for a reason. I don't think that they're going to be that difficult for you to pick up, even if you don't see me present them. I think it's really important for us to get the first 4 down. And then in the optional content, I'll finish the rest, mainly just for completion. Oh yeah, and then extra content, that's always there. Okay, cool. So quick introduction to quantum key distribution. let's start off with knocking the quantum off of that, right? What is just key distribution in general? It's a term or a procedure used in cryptography. So the whole point here is that we want to have Alice and Bob being able to communicate with each other without being eavesdropped, right? And eavesdropping just means if Alice sends a message to Bob and some other party wants to try and listen in. So for example, if I want to send my password to a banking website, I want to be able to do that without other people listening in and figuring out what my bank password is, right? So that's what the point of this is. The point of this is to try and establish what we call a secure channel. So that just means that Alice and Bob are communicating and other parties cannot see what they are saying. Now, quantum key distribution doesn't directly allow us to do that, but it is sort of the first step. So what quantum key distribution is going to allow us to do is establish a shared key between Alice and Bob. And that key is going to be random. So just to repeat that again, we're going to establish a shared key. So a key is just a sequence of ones and zeros that Alice and Bob have. So they both have the same sequence of ones and zeros. That sequence of ones and zeros is random, right? So there's no pattern to it. It's just some random string, but both of them have the same string. And throughout this whole process, Alice and Bob never have to meet each other, right? So Alice and Bob can be all the way across the world. Remember in super dense coding how the first step, we needed Alice and Bob to be in the same place to prepare an entangled state, and then they traveled apart. Well, here in QKD, they're going to start apart and they're just going to stay apart, right? So when they start off apart, they never get to meet in advance. How do they both establish some random string that they agree on and that nobody else knows? So again, just to summarize, a random string of bits where Alice and Bob both have the same string, they're not allowed to meet beforehand, and that string has to be secret. Given that, there are ways to communicate securely, to do that sort of secure channel communication that I talked about before. We're not going to go into detail on that, but it's honestly a very simple extension. If you already have these keys that QKD is going to give us, then you can use something, in the simplest case, you can use something called a one-time pad that allows you to do secure communication. But we're not going to worry too much about that. The goal for us today is to establish these shared, secret, random keys. So that's pretty much what this whole introduction section says, is just a textual description of what I just said. I actually want to pause there and just, does anybody have questions about what the sort of goal of QKD is or what this algorithm is supposed to do? Because I think that is important. So somebody asks, would we consider this as a public or private key? Good question. So I would say neither. Public and private keys are terms that are usually used in what we call asymmetric cryptography. So in asymmetric cryptography, the key used to encrypt a message, so in other words, to turn it into a form where it cannot be read by an eavesdropper, and then decrypt it by the intended recipient, those two keys are different. So QKD is usually used in what we call symmetric cryptography, and that means that the key used to encrypt and decrypt is the same, right? So in this case, the key held by both Alice and Bob is going to be the same. And so it's not really a public or a private key. Yeah, so somebody asks, does the key have any information about the message? No, right? So the key distribution step has nothing to do with sending the message. That's called the one-time pad. But in order to use a one-time pad, you need to have these shared, secret, common, random keys. And that's the part that we're going to be doing here. Because honestly, I mean, you can look it up if you're curious. One-time pad, take my word for it, really simple. The difficult part of one-time pad is how you prepare these keys. And that's what we're going to be looking at today. So somebody says, what does it mean for the security to be guaranteed by the laws of quantum mechanics? Right, good question. So this is one of the benefits of QKD, certainly, over other types of key distribution. If you use a classical computer for key distribution, the very best algorithms we have are not entirely secure. right? So we could establish these shared keys, but we wouldn't have any 100% guarantee that somebody else doesn't also know it. So that guarantee of secrecy might not be there. What gives us good confidence in secrecy is just really difficult math problems. So we say, for example, factoring prime numbers, well, as long as the eavesdropper cannot efficiently factor prime numbers, then our communication is secure. But it's still not 100%, right? There's still a chance that your eavesdropper could have massive computing resources and factor the prime number. Or maybe they just get really lucky and they figure out the factors to the primes, right? Here, we're not relying on the difficulty of any math problem. We're literally relying on the rules of quantum mechanics. So it's pretty much saying, as long as all the stuff we've learned about superposition and measurement and entanglement, as long as all of that is true, it doesn't matter how much computing power your eavesdropper has. They could have a supercomputer 1,000,000 times bigger than the biggest one on Earth, and it wouldn't help them. This is 100% secure and secret, as long as the rules of quantum mechanics are correct, which we think they are, which is honestly really cool. It's a very powerful claim that you can establish the secrecy with perfect guarantee, right? 100%. Yeah, so somebody says, can I talk a bit more about one-time pad in the optional content? Absolutely. I will write that down. And they ask, is symmetric and asymmetric, is one better than the other? It depends on the application, I guess. Generally speaking, asymmetric is what we usually use because it's easier, like doing asymmetric cryptography tends to be easier than establishing these shared keys. Establishing these shared keys is really, really hard without a quantum computer. And even with a quantum computer, it's kind of challenging. So at least to the best of my knowledge, symmetric is not usually used as much just because establishing these shared keys is really difficult and expensive. But if you wanted to be extremely certain about the security of your encryption and your message that's being sent, then symmetric would probably offer you a better guarantee. Okay. Oh yeah, sorry. So somebody asked if they are primes, how do they have factors? I mean, finding the prime factors of a composite number, exactly. So thank you for clarifying that. Can anyone let me know, why are we into encryption and stuff in quantum computing? TLDR, I didn't attend the lecture. Good question. Encryption and cryptography is one area where we think quantum computers might be able to, I guess we'll say, impact the world in a big way. Not for a very long time, right? Shor's algorithm is the famous one, of course, but there's lots of other ways that quantum computers could be used for encryption and cryptography that are very interesting. So I guess there's not really a direct reason why this is the case. It's just that quantum computing is often applied to cryptography. And so as we're introducing you to the field, it makes a lot of sense for you to be familiar with these ideas. Right, let me throw the access code on my screen here. I still don't really have a better way of doing this, unfortunately. We'll do access code 7048. Okay, let me answer one more question here. Is this encryption for other than non-entangled pairs transmission? So this encryption would be for transmitting a classical message. So just a sequence of bits that you want to send to another person without anybody else finding out what that sequence of bits is, right? So that's a fair point. We're not talking about transmitting quantum information here. We're talking about transmitting classical information encrypted. Okay, so let's move on to the actual algorithm then. I guess here is a brief overview of what's going to happen. There's 7 steps, so obviously quite a bit longer than superdense coding. That's okay. We're still going to go through steps 1 through 4 in the lab today. Step 1 is to, well, actually steps 1 and 2 are fairly similar to each other. Both of them is effectively Alice and Bob sitting there. They're going to generate some random numbers. In Alice's case, she's going to need 2 random bit strings. One for, well, the actual bits she's going to send, and then one for the basis that she's going to send them in. I'll talk more about that when we get there. Bob is going to require a random bit string that defines the bases he's going to measure the qubits in. So the first 2, are theoretically, like conceptually, I guess, harder to understand. But practically all that's going on here is Alice and Bob generate some random numbers. Okay. They don't have to communicate with each other. They literally just sit on their own computer, generate some random numbers. In step 3, Alice is going to use her random bit strings to create some qubits, right? So she's going to create a sequence of qubits using her random bit strings. And then she's going to send Bob those qubits. So here we have transmission of quantum bits, qubits, to get those bits over to Bob. Now, we're also going to refer to these things called a, oopsie, that's not what I meant to do, a quantum channel. And there's also going to be a classical channel that comes into play in the optional content. Now, these things are basically just, it's a fancy word, right? Like channel is used a lot in cryptography. All it means, though, is some means of transmitting quantum or classical information. So a quantum channel, as we talked about last week, it could be a fiber optic cable, right? And you could send photons that are qubits through the fiber optic cable. Or if you wanted to transmit ions that were in superpositions, maybe that would be a bit more difficult, right? A classical channel, well, those exist all over the place. That's how our internet works. That's just anything that allows you to transmit classical bits from one location to another. Okay, so I'll go over the last 3 steps once we get to the optional content, but for now, we're just going to focus on the first 4. All right, so, oh, actually, I think I'm just going to restart and clear all output here to make sure that we have everything we need. Yeah, okay, this is good. Okay, so first up then, we're going to run our import statements, right? So we have our get rand bits that we talked about in the slides. We're also going to import Qiskit. We use a slightly different notation here, which I'll point out when we get to the actual code that uses it. But no worries, it's the exact, like it functions the same as what we've seen previously. So I'm going to go ahead and click run on this. And once the star turns into a number, we know that we're good to go. There we go. Okay, so before we get into the protocol itself, we have to establish a few parameters on the experiment. So I'll just go down here and tell you what they are. The key length is how many random bits we want to establish. So again, the point of key distribution is to establish these random shared secret keys. And a key is just a sequence of 1s and 0s. So in this notebook, we're going to generate sequences of 500 bits, 500 1s and 0s. Then we're going to have these 2 things, the quantum channel and the classical channel. Those are going to be empty for now, but as we go through the notebook, we're going to send things, so to speak, through these quantum and classical channels to simulate transmitting them physically in real life. Again, I'll talk more about that when we get there. Okay. So with that, let's jump right into things, beginning with step 1. In step 1, Alice needs to randomly select a bit key and a basis in which to encode each bit of the bit key. So here, the first step is effectively 2 parts for Alice. Alice needs to generate a random bit string. So if we want a 500-bit key at the end, Alice is going to generate, well, I guess it doesn't exactly work this way, but we said that our key length was going to be 500, right? So let's say that Alice is going to go ahead and generate a 500-bit long random bit string. So again, this is just going to be 500 random 1s and 0s. She is eventually going to turn those into qubits, right? So if the sequence started off 0, 1, 1, 0, she would turn it into something like ket 0, ket 1, ket 1, ket 0, right? That's the idea here. But that would be encoding in the Z basis, right? So if Alice sees a 0 in her bit string, she's going to turn it into ket 0, which is one of the eigenvectors of the Z operator. If you think back to when we talked about eigenvectors and eigenvalues, there's another possibility though. Alice might encode in the X basis. So when she encodes in the X basis, a 0 becomes ket plus and a 1 becomes ket minus. right? So again, that's because ket plus and ket minus are eigenvectors of the X operator. So for every one of these 500 bits in Alice's initial key, first she has to generate 500 random classical bits to tell her whether she's going to do a sort of 0 or 1 encoding. Then she's also going to have to generate another string of 500 random bits to tell her whether each encoding is in the Z basis or the X basis. That all sounds complicated, but the short version is that she has to generate 2 random strings of length 500. So let's go ahead and do that. I've started off with some skeleton code just because there is a lot of code to write in this lab. I'm not going to be writing all of it down. Instead, I've sort of filled in most of it and left some pieces for you to fill in. So I'll ask for some feedback at the end on how you like this format versus how I usually do things. But for now, we're going to define a function called select encoding. It's going to take as an argument the length of key that we want to create. So in this case, that's going to be 500. As I said, Alice needs to generate 2 random strings of bits, right? So one we're going to call her bit string, and one we're going to call her bases, right? Because a 0 in here means the Z basis, a 1 in here means the X basis. Okay. Now, for I in range length, so all this does, that's going to execute this loop 500 times. We want to use the function getRandBits to generate either 0 or 1 randomly. And we want to iteratively build up these 2 bit strings. So I'm going to throw this over to a Zoom poll and ask you all what code you think should go here where it says Zoom poll. Now, I will say this is a multi-select, so it's possible that there are several correct answers that go in the for loop here. I will give a few seconds for everyone to read all the options and make their selections, and then I will move on and share the solution. In the meantime, let me just take a quick look at the chat. Okay. So if you're still stuck on this question, I'll give one hint as we wait for a few more people to answer. There should be 2 lines of code in this for loop. So in other words, you should check off 2 of the options in this question. Okay, so why don't I go over the answers now? I will leave the poll open as I keep going over this. So as I said, we want to build up these 2 bit strings iteratively. Now, the way we're doing it here is we're running this bit of code inside the for loop 500 times. So for each of these 500 bits, we want to tack on a new 0 or 1 to both of our strings up here, right? Both of these are just independent, totally random sequences of bits. So if you think back to the slides, these things here are strings, right? They're just empty strings because of these double quotes. And think back to the slides, how you append to a string, right? How you appended to a string was using plus equals. So I'll start off with Alice bit string. And then the code here is plus equals. Oops. And then we have to do getRandBits. And as I said, in this lab, we're always just going to get 1 bit at a time, right? So we have a 1 here because this whole code, this whole loop is being run 500 times. Now, we also have to convert this to a string, so I'll just add stir around that. And that is going to build up Alice bit string 1 bit at a time, so we get to a length 500 string as the result. Now, for Alice bases, we're actually just going to do the same thing. There's nothing different here. Alice bases plus equals stir get rand bits 1. And again, the reason for this plus equals thing is just so that we sort of glue on these new bits onto the end of the string each time we execute this loop. So these should have been the 2 correct answers for that question. And I will go ahead and run this to give myself that function. Okay, let me just look at the chat real quick. Where is length defined? Yes, so length is a argument to the function, right? So when we eventually call this function, we'll have to tell it what the length is. And as you said, that length is just going to be capital key length, the thing we saw before. But yeah, that's where this length thing is defined here. The access code is in the top left here of my screen. Okay, let's move on. Oh, somebody says, why do we state for I in range? Yeah, so you might notice that we never use this I thing. Pretty much all we're using this loop for is to just execute code 500 times, right? So we don't really care what I is. We're just going to run this exact same code 500 times. That's what this loop is doing. You could call this variable anything you want. You could call it irrelevant because, you know, it's irrelevant, but we can just call it I. Okay, so let's go ahead and run this code. So here I'll show how to invoke this function. You'll notice that we return these 2 things using a comma to separate them. That's fine. To call that, you just use commas on the left-hand side of your assignment. Right, so here we're going to have Alice bit string and Alice bases equals select encoding. That's the function we just created. And we're going to pass it 500 as the length. Then we're going to sort of preview the first 10 elements of each just to make sure it looks reasonable, right? So it should kind of look like 10 random bits, and the 2 strings should be different because they're 2 totally random strings. Okay, here we go. So we have our first random string and our second random string. It's actually quite surprising that we got 7 zeros in a row here, but I think it's okay. These things look fine. Okay, step 2 is very similar. So here we're just going to have Bob do basically the same thing, but Bob only has to select bases, right? So whereas Alice before had to create a bit string and create a whole bunch of bases, Bob is only going to have to create bases because he doesn't have to prepare any qubits. He's going to receive the qubits from Alice. So this function here, select measurement for Bob, looks pretty much the same, right? We start off with 1 empty string. We do a loop 500 times. We add on these get rand bits, and then we're going to return Bob's bases. So I'm going over this pretty quickly just because it's the exact same code as what we saw for Alice. I'll run this. And I forgot to run the function. Oops. So I'll do that. And then I'll run this one. OK. So we can see Bob's string here is another random set of zeros and ones. It is not the same as either of Alice's. Right? So all we've done in these first 2 steps is effectively generate 3 strings of 500 random bits. OK. Now, step 3 is the hard one. We only have 5 minutes left in the lab, technically, but I am going to try and take my time a little bit with this because the encode step is the most important one. And I also forgot to end this poll. Oops. I can share the results here as well, in case people are curious. OK, so let's look at how these random strings of bits are actually used now, because I think this is the confusing part for sure. OK, so as I said before, this step for Alice is she's going to prepare a whole bunch of qubits. Now, which qubit or which state she prepares depends on her two strings. So again, we have two strings of 500 random bits. Alice is going to consider each, I guess, index in that string separately. So she'll look at the first bit in her bit string and the first bit in her basis string, right? And that's going to allow her to figure out what qubit she should prepare. Now, this table here gives a really good summary of what's going on. So again, Alice is going to look at the first bit in her bit string, and it's going to be either 0 or 1. And then she's going to look at the first bit in her basis string, and that's also going to be 0 or 1, right? So there's 4 possibilities here total. And what these values of these bits are is going to determine what qubit she prepares. So if they're both 0, she does a ket 0. If one is 0 and the other is 1, she does ket plus. If it's 1, 0, she does ket 1. If it's 1, 1, she does ket minus. So again, what's going on here? Let me just actually give myself a cell here. So if Alice bit string equals, say, I'll just generate some randomness myself. So again, this is not intended to be the same as what we saw earlier. This is just me doing an example. The way this is going to work is the following. Alice is first going to look at the first bit in each of her strings. And we see that those first bits are 0, 0. And so what she's going to send is first going to be ket 0. And again, I got that just by looking up the 0, 0 entry in this table. It gives me ket 0. Okay, next up, we have a 1 in the first string and a 0 in the basis string. So we go to our table, we find 1, 0. That's going to translate to ket 1. Okay, now we go on to the third element. The third element is also 1, 0. So that's also going to give me ket 1. Let's look at the fourth one. We have 0, 1. So again, I go to my table, 0, 1. That'll give me ket plus this time, right? And so on and so on. So as you can imagine, for a string of 500 bits, this would take us quite a while. That's why we're going to write some code to do it for us. Let me just hop over to the chat, because I think this is a bit of a difficult concept. Is the optional content also recorded? Yes. Why the lab time is different today? Because here in North America, we use an arcane thing called daylight savings time, unfortunately. Okay, so does anybody have questions about this encoding protocol? Because I feel like if you understand how Alice and Bob use their bit strings, right? So effectively how Alice goes from these two bit strings to her quantum states, that's really the core part of QKD. If you understand that, you're in a good position. So does anybody have any questions about how I did this translation from these bit strings to these quantum states? Okay, so somebody says, I did not understand encoding. Same here, I also didn't understand encoding. Okay, so by the way, when I say encoding, that term, it's a very generic term, right? But all it means in this case is sort of going from classical bits to quantum bits. Are the encoding rules always the same as mentioned here, or do they vary? They're always going to be the same as what's mentioned here. Yes. So you can always use this table here to determine what your encoded qubits should be. Still unclear why we need the bit string and the bases. Sure. So to answer quickly how we go from classical bits to qubits, again, we just look in our table, right? So we have these two classical bit strings, and we go one at a time. We're going to look at the first bit in each string. We see it's 0, 0 here. So we're going to look at the 0, 0 row in our table to get the encoded quantum state. right? And then we go to the second bits here. We see it's 1, 0. So we go to the third row in our table. That's a ket 1. What's the rule I'm following? So I'm looking at sort of the bit in this string. So I always pick the same position, right? So it's always going to be the first bit in each string, the second bit in each string, the third bit in each string, etc. And so, for example, with the third bit in each string, we have a 1 in Alice bit string and a 0 in Alice bases. And so I look at the row that has a 1 in Alice bit string, a 0 in Alice bases, and then I look at what the qubit should be here, right? And then I will put ket 1. Okay, and then somebody said, I'm unclear why we need both the bit string and the bases. So the reason for that is just that there are 4 possible qubit states that Alice could prepare for every bit in these strings. And so we need 2 bits to determine which of these 4 choices she should encode. Oh yeah, so somebody says, shouldn't we also follow the right to left rule here? In this case, no. So in this case, we are just going to do it sort of as easily as we can, reading from left to right. That's also why you'll notice I didn't write this as, well, I guess it doesn't really matter. But yeah, we are just going to go left to right here. The reason we can do this in this case is because, well, actually, I won't go into that. But yeah, left to right is okay in this case. Is this encoding just a standard or a choice of convenience? Right, this is just a standard. You could make this table however you want. This is just the standard way that it's usually done in QKD. Is the table here required to be memorized to do encoding? Pretty much, yes. I guess I don't think you actually need to memorize it. You can always have this notebook open with you when you're doing the homework questions, for example. But I would definitely recommend having this table with you because it's everything you need to do this encoding. Okay, so somebody says Alice bases is dependent on her bit string. So I just want to clarify, I guess, these 2 strings are independent. They do not depend on each other. They're totally random. And so when we create each qubit, so for example, our first qubit depends on the first bit in both Alice bit string and Alice basis, right? Okay, I'm glad to hear some people are getting this. Yeah, so I mean, ultimately, all you're doing here is you're looking at the first bit in each string, and then you're going to your table, and you're looking up what the associated qubit is. Somebody says, is there ever a case where you might choose 3 states instead of 2? I guess in theory, yes. I'm not really sure of any protocols that actually use that, though. So I guess the short answer is I'm not sure. Oh, interesting. So somebody says in lecture, the random bases was not created. So that's why some people are confused. Interesting. So I wasn't at the lecture, so I'm not sure how they might have done it, but yeah, I don't know how you would do this without the bases. As far as I know, you always need to do it this way. But perhaps it was taught in a slightly different way during lecture. Okay, so any other questions on this encoding step? There is still a little bit more because we're going to have to write this as a Python function, which looks large and scary and intimidating. I agree, but I think it's most important to just figure out how you would do this by hand, because then turning it into code becomes a little bit less daunting. Oh, I see. They used arrows to do it. Okay, okay. Yeah, so another way to think about this, I guess, instead of these 4 qubits being sort of ket 0, ket 1, ket plus, ket minus, you could think of everything as being up, down, left, right, as being arrows, right? And then the bit in the first string is going to be whether the arrow runs vertically, up, down, or horizontally, left, right. The bit in the second string would be, if it's vertical, is it up or down? If it's horizontal, is it left or right? Totally equivalent way of thinking about things. I think it's probably a little bit more complicated. I would encourage you to just use this encoding table as I've sort of described it here, and just go methodically for yourself. Look at the first bit in both strings. You see it's 0, 0. So you go to that row in the table and you get the qubit. Then you go on to the second bit in each string. You go to the table, you get your qubit, etc. Cool. Okay, I am glad I'm clearing this up for people. So somebody asks, how would you determine this encoding without this table? You need the table. So I guess I said before that Alice and Bob don't meet beforehand. They do have to agree on how this encoding is done. So this is the one sort of shared piece of information that you do need. So it would be impossible to do the encoding without this table. Okay, any other questions? Okay, awesome. So if all that is clear, then we should be ready to write this as a Python function now. Now, large function, I agree, but I promise it is just doing exactly what I just described, right? So again, we're starting off with def to define a function in Python. It's going to be called encode. And as our two arguments, we're going to get the bit string and basis string that we just talked about. Now, the encoded qubits is a list where we're going to store each of our qubits. So for example, up here, when I generated ket0, what we're going to do is we're going to append that onto our list, right? And then when we generate ket1, we'll append that onto our encoded qubits, and so on and so on. This for loop here is going to run through all 500 bits in our key, okay? And now for each one of those bits, we're going to do the following. So this is kind of like, okay, I'm going to consider only the first bit of each of my strings. We're going to create a new qubit. Now to do that, we're just going to make it a 1 qubit, 1 classical bit quantum circuit. I'm going to call this a qubit though, because it really is just the same thing. And then we just have a big conditional. So this is the sequence that I was going through above. If the first bit is 0 in the first string and the bit is 0 in the second string, then we're going to encode in the Z basis a 0. Okay, so again here we would go to our table, we look for 0, 0, and we see it should be a ket0. Now remember, when you create a quantum circuit in Qiskit, it always initializes as 0. So in this case, we actually don't have to do anything else here. We just pass. Remember, that's the keyword in Python that just means do nothing. Okay, what's the next possibility? If we have 0, then a 1, what should happen? Well, let's go back up to our table. 0, then a 1. In this case, we want to do a ket plus. Okay, so our quantum circuit starts off in ket0. We want to create ket plus. What gate should I use here to create ket plus? We're going to do something. We're going to do QC dot. How do we turn ket0 into ket plus? That's going to be an H gate. Right, so this is something we've seen before, that when you apply an H gate to ket0, you will get ket plus. Okay. Oh, thank you. Yes, somebody just pointed out in the chat. The outer is the basis. Oh, okay, that's kind of annoying. Okay. Yeah, you're right. So the order that this is being compared is opposite to what I did above. Right, so notice how above I was looking at the bit string first and then the basis. Now we're looking at the basis first and then the bit string. So yeah, I'm sorry, I'll have to reverse that. So here, it's not going to be qc.h. We're actually looking for the row in our table that's 1, 0. If we look for that row, that should be a ket1. Thank you for pointing that out. Yeah, that's my bad. Okay, so if we want to go from ket0 to ket1, what do? It's again a single gate, but Hint, hint, it's not going to be an H gate. Exactly, it's going to be an X gate. Okay, awesome. Now let's fill in the rest of the possibilities. If the basis is 1 and the bit string is 0, let's go back to our table. Again, it's going to be reversed now. Basis is 1, bit string is 0. That's the second row. And so we're going to do a ket plus. And I kind of already gave away the answer here. In order to do ket plus, we're going to do qc.h. Okay. Now, I left the most difficult question for all of you. If the basis string is 1 and the bit string is 1, let's go to our table. That's the final row here. We're going to need ket minus. My question to you is, which gate should we apply to get ket minus? So I'll pop up a Zoom poll for this. I'll let you consider the options, and then I'll go over the answers in a moment. Again, this is one of those questions where there could be multiple correct answers, right? So feel free to check off all of the lines you think should go in this if-else statement. Oh yeah, that's a good point. So somebody asked me to update this function to match the ordering of the text above so it's less confusing. I will do that. Absolutely. I think that's a good idea. Yeah, I know that your notebooks have the answers in them. I don't know. You can still try and think about it if you want, but that's okay. It's not like these polls count for anything. It's more just so that hopefully you have a chance to think a little bit on your own. Okay, so I'll chime in with a quick hint here again for anybody who's still looking at the question. There should be 2 correct answers here. Okay, so let's go ahead and look at what the answer is. Now, one of the answers is pass, right? And I will immediately sort of eliminate that as an option because if we just passed here, we would still have ket 0, but we want to have ket minus. Okay. Now, how do we get ket minus? Well, in my opinion, I think the easiest way to think about this is to think about the only gate we've really talked about that can give you ket minus, right? If you think about where we've seen that state before, it's what happens when you apply a Hadamard gate to ket 1, right? The Hadamard gate, the H gate, turns ket 0 into ket plus and ket 1 into ket minus. So what we'd like to do is have a ket 1 state and apply a Hadamard to it. Well, let's back up again then. How do we create a ket 1 state? Turns out we can just use the X gate, right? So if I do qc.x, that's going to flip my 0 to a 1. And then I'm going to do qc.h to turn that 1 into a ket minus. And that should work. Now, the only other choice here is what do we pass as the arguments to these functions? Is it 0 or 1? Well, this is a bit of a trick question because our quantum circuit only has 1 qubit. And so because our indices start at 0 in programming, these both have to be 0. If you tried to put a 1 in here, it would give you an error because there is no Q1. There's only Q0. Okay, so hopefully that was all right. That is kind of like the hardest part of the encoding step. And I will say as well, decoding looks pretty similar. but I will go over it, of course, in the optional content. Okay, so we've written this huge function for ourselves. I'm going to go ahead and run this cell so we have that function. And then I'll just quickly show how to run this. You would create your encoded qubits list. You call encode, pass in those 2 bit strings, and we have what we need. Oh yeah, good question. So somebody says, could you use an H and a Z gate? Yes, so I should mention here, there are several correct answers. That is a good point. For starters, you could swap the order of these 2 operations, right? If you swapped the H to go first, you would then have to have H followed by Z, right? If the H comes second, you do X then H. Both of those are valid responses. That's a good point. Is encoded qubits an array of qubits? Exactly. Yeah, so sorry, maybe I should have gone over that part a little bit more. So once we do our gate on our quantum circuit, so we end up with whatever state we want, then we're going to use that append function to add that qubit into this list. And so when we return encoded qubits, that is indeed going to be a list of quantum circuits, which in this case, each quantum circuit is just 1 qubit. So I'm just calling them qubits. Yeah. Alrighty. So that's the end of step 3. And I know that we're over time, but step 3 is definitely the most difficult one, I think, to understand. Encoding and decoding are the 2 difficult pieces of this algorithm. So I wanted to really go slowly through that. All right, step 4, pretty easy, because step 4 is now that Alice has encoded all of her qubits, she's got this big list, now she sends them to Bob via some quantum channel, right? Just like in superdense coding, this quantum channel could be a variety of things depending on what types of qubits you're working with. So for our case in the programming world, we're just going to assign it to this quantum channel. And we're going to say that this essentially represents sending those qubits off to Bob. Now, crucially, when Alice sends these qubits to Bob, an eavesdropper might be able to see them, right? It could be the case that somebody trying to intercept their secret shared key sees all of these qubits. Turns out that doesn't matter. Even if the eavesdropper sees all these qubits, we can still guarantee secrecy. And I can talk more about that toward the end if you want. So somebody asks, can the quantum channel be a teleportation protocol for each qubit? Yeah, great idea. And it turns out, yes, you can absolutely do that. Instead of having a way to physically transmit the qubits, you could instead use quantum teleportation, which we learned about last week. Yeah. Cool, cool. Okay, so I'm going to go ahead and run this cell. So now Alice has sent her encoded qubits to Bob, and we are good to switch over to Bob's side, because everything we've done so far, well, I guess the first 2 steps were Alice, then Bob. Step 3 was all Alice. Step 4 is all Alice. Now in the optional part, we'll talk about how Bob makes any sense out of this. Okay, so this brings us to the end of the required content. I'll just quickly mention some key takeaways. Key distribution, as I said, is an essential step in secure communication. It is the difficult part of establishing a secure channel. QKD basically has 3 steps. So first, Alice is going to generate a sequence of qubits. We saw how she does that. And then she's going to send them to Bob. Next, Bob measures them. We haven't done that yet, but we'll do it in the optional content. And then finally, Alice and Bob compare their bases to figure out which bits match. Final key takeaway, we use Python functions to code each of the steps just to make our lives a little bit easier. As always, there is some further reading here on QKD. QIS, by the way, is a quantum information system, just kind of another name for a quantum computer. And then all we have left is the optional content. So why don't I pause here and I will throw up the post-lab Zoom poll. That is the end of the optional content. So please go ahead, fill out this poll. And then if you do have to leave, no worries, you can head on out. The rest of this lab is recorded if you ever run into confusion with the decoding part of QKD. So I'll just give 30 seconds or so for everyone to fill out this poll. And then after that, I will be moving on to the optional content. So if you have to head out, thanks for joining us, and I'll be back in about 30 seconds. Okay, so let's see. I'm just going to go over to the chat and see if there's any quick questions. Somebody asks how to use draw here. That's a good question. So you could draw each of the individual qubits, right? So for example, I could do encoded qubits. If I wanted to draw the first qubit, for example, I could do dot draw on that. So again, this square bracket just means sort of select the 0th qubit. If I go ahead and run that, you'll see it shows me that, okay, the first qubit apparently was supposed to be ket 1, right? Because we had ket 0, then we use an X gate to turn it into ket 1. There's no direct way to draw the whole circuit, though. And in fact, drawing a circuit with 500 qubits would quickly become pretty unwieldy. So there's no direct way to draw everything, but you can draw the individual qubits if you want. So another student commented on the idea of using quantum teleportation to do this transmission of qubits. And they said, if they're eventually teleporting, first they need to meet at one place anyway. So when they are meeting each other, can't they just talk and do the discussion, which they're going to do on the communication channel? Yes. So doing quantum teleportation to establish a QKD, secret key, and then doing one-time pad and all that kind of stuff is kind of overkill. It would work though, right? In theory, it would work. There's no real reason you would do it, but I think everything says it should work fine. Okay, so let's move on to, oh, sorry, one more question. Would this circuit be represented by the tensor product of 500 states? Could we even call this a circuit? Technically speaking, yeah, it would be the tensor product of 500 different states. I guess yeah, no, that's exactly what it would be. You could call it a circuit. You could call it a 500 qubit circuit. That would just be very large. Now, I guess the reason we haven't put it together as a 500 qubit circuit here is because we never do anything between the qubits, right? Notice that everything we're doing is just 1 qubit gates. We never do anything like a CNOT, for example. So we don't need all these qubits to be in the same circuit. They can each be their own little independent circuit. That is just fine. Okay, so why don't we move on to the optional content? So the optional content should feel like a pretty straightforward continuation of what we just talked about. We ended off with step 4, so let's move on to step 5. So as a refresher of what's happened so far, Alice and Bob both created random strings of bits. Alice had 2 of them, and she used these 2 random strings of bits to generate a sequence of 500 qubits, right? And again, by that encoding step was just by looking at the table to find out what each qubit in that sequence should be. Okay, now she has sent her 500 qubits to Bob, and now it's Bob's turn to do something with them. So in step 1, Bob already generated a random string of bits, 500 bits. Those bits, in this case, is going to define which basis Bob measures each of Alice's qubits in, right? Because remember, when Bob receives all these 500 qubits from Alice, he doesn't know what states they're in. He has no idea if it's ket 0, ket 1, ket plus, or ket minus. He just has these qubits, and in order to learn anything about them, he has to measure them. But remember, in quantum mechanics, you have to choose which basis to measure in. And that's a choice that Bob has to make without communicating with Alice, right? So what we're going to do here is Bob is just going to make a random choice. for every qubit, he's essentially going to flip a coin and say, if it's heads, I'm going to measure in the Z basis. If it's tails, I'm going to measure in the X basis. And do that for every single one of Alice's 500 qubits. That's what this function does. So let's take a look at what's going on here. We're going to call this function measure, and it's going to take as inputs Bob's bases. So remember, this is a string of ones and zeros, 500 ones and zeros. And I said before, it's like Bob flipping a coin. That's pretty much how you can think of it, right? The first bit is going to be, say the first bit is a 1. That means he lands on tails for the first coin flip. The second bit is a 0. Maybe that means he lands on a heads for the second coin flip. So this Bob bases bit string represents all of Bob's coin flips. Then he also gets the encoded qubits, right? So this is all 500 of Alice's qubits. And then we're also going to take a Qiskit backend here so we can actually execute our code and get some results. Okay, so let me just check the questions that popped up. If there's anything. Let me see. So somebody asks, quantum teleportation sends 2 bits instead of a qubit. Does it require them to actually meet up? So yes, quantum teleportation, because it's sort of like the reverse of superdense coding, the first step is that Alice and Bob need to share an entangled state. And the way to do that is they have to physically meet up, prepare the entangled state, and then they both leave with 1 qubit, right? So teleportation is going to start the same way. You have to prepare an entangled state, and you have to share that before you can start the rest of the algorithm. Can I explain the measurement once again, please? Sure, yeah. So to review what's happened here, Bob receives 500 qubits from Alice. But because they're qubits, Bob doesn't know what state they're in, right? He doesn't know if it's ket 0, ket 1, ket plus, or ket minus. In order to know anything about the qubits, you have to do a measurement. And remember when we talked about the Stern-Gerlach experiment, for example, when you measure a qubit, you have to decide what basis you're going to measure it in. So here, for every one of Alice's qubits, Bob is going to flip a coin. If it lands on heads, he's going to measure it in the Z basis. If it lands on tails, he's going to measure it in the X basis. Now, notice the basis Bob measures in is not necessarily the same as the basis Alice prepared the qubit in, right? So Alice might send him a ket plus, and he might flip his coin, get a heads, and measure it in the Z basis, in which case the output is random, right? Ket plus measured in the Z basis is 50% 1, 50% 0. So Bob's bases do not necessarily match Alice's. On average, half of them will match and half of them won't. Okay, any other questions about sort of like the high level idea of measurement? Because I do think it's important to get the high level idea before we try and code it. Yes. So the question then is, how will Bob get the exact message that Alice sent? We'll talk about that. That's going to be step 7. So when he does his measurements here, I guess, just to be clear, when he has the 500 qubits from Alice and he flips all his coins and does the measurements, he is not going to get Alice's bit string, right? Because if his basis did not match what Alice's basis was, then he's going to get 0 or 1 randomly. And so that might match Alice's bit string, but it also might not, right? So at the end of this measurement procedure, Bob is going to have 500 measurements, but those might not be the same as Alice's original bit string. So we're going to have to do a couple more steps so that they have the actual exact same string. But we'll see what those are in a moment. It's a great observation, though. Yeah, because these bases are different, the bit string he gets at the end of this will not be the same necessarily as Alice's. Okay, eagerly awaiting the conclusion. All right, let's go through this function then. All right, so I talked about what the inputs are. We are going to create an empty string here. I guess just to be consistent, I'll use double quotes, although single quotes also works. And we're going to build up this bit string in the same way. So for every measurement, right, Bob is going to flip a coin, measure in a basis, and the basis measurement is either going to give him 0 or 1, right? And then we're just going to keep tacking those on to Bob bit string here. Okay, so we go into a for loop. So this is going to run 500 times. The first thing we do is we get a hold of the ith qubit, right? So the first time this loop runs, this is going to be the first qubit that Alice sent Bob. Now, Bob flips a coin. So if he lands on heads, we want to measure in the z basis. If he lands on tails, we want to measure in the x basis. So I've left some blank space here for what we want to fill in. Measuring in the z basis is pretty easy because that's the default in Qiskit, right? So we can just do qc.measure the 0th qubit onto the 0th classical bit, and that's going to give us a z basis measurement. What about the x basis? Because Qiskit, if you remember from even way back when we did the circuit composer, Qiskit doesn't let you directly measure in the x basis. Instead, you have to translate from the x basis back to the z basis and then do a measurement. So how do we go then from the x basis back to the z basis? That's really the question here. Hadamard, yes, you're correct. So we do qc.h on our qubit. There's only one here, so it's q0. That is going to bring a ket plus back to ket 0, a ket minus back to ket 1. And now we're in a position to do a regular qc.measure. Cool, cool. Okay, the rest of this I left in here because it's pretty much the same as what we have seen before. We execute our job. We use whatever backend was specified. Here we've specified SHOTS1 just to kind of simulate how this would work in the real world, because when Bob receives one of Alice's qubits, he's only got one shot to measure it, right? Once he measures it, it's going to collapse and he can't measure it again. So we're only going to have the simulator do one measurement. We get our result, we get our counts. And this line here is a little bit of magic that basically just deals with any experimental noise, okay? So I'm just going to skip over this largely. It's not that important to understand, but you can think of it, well, I guess it literally does nothing if you have one shot here. So for our purposes, you can pretty much just ignore this line. What we're looking at is which bit was measured. Did we get 0 as the result, or did we get 1? Okay, and then we're just going to append it. So once we've done our measurement in either the z or x basis, we're going to append that to our bit string, do that 500 times, and then we're going to return whatever all of our measurement results were. Right, yes. So good question. So there's a comment here to increase the number of shots if you're running on hardware. This just means if you wanted to try this same circuit and everything on like an actual quantum computer, right, on hardware, it would be wise to use a few more shots here because hardware can introduce a type of error that will make this algorithm fail. Now, there are ways around that, of course. This can be used in real applications and in real experiments. The algorithm just becomes a bit more complicated if you're trying to deal with these additional types of hardware error. So if you want to run this on actual hardware, I would recommend increasing this. You can go to like still a small number. You can do maybe 32 shots, and then it should still work. If you're using a simulator, though, you can just use 1. The simulator is always going to work on that first shot. So this is fine as long as we use the simulator. Why do you need the max function? Yeah, so I guess I'll talk briefly. If we were running on hardware and we went to 32 shots, for example, because of hardware error, it's possible that when we measure ket 0, maybe we get 0 31 times, but we might have one erroneous measurement that just because of some fluke in the hardware, we measured ket 0 and got a 1. Clearly, that's not supposed to happen, but sometimes it does because quantum computers are imperfect. So what this max is going to do, it's basically going to say, maybe we don't measure the same thing for all 32 experiments, but we're going to take the majority. Whichever result got measured more, so in that case, 0 was measured 31 times, it'll set measured bit to be 0. So it's basically like doing a majority rule here. Anyway, for us, we're just going to stick with one shot, and this max thing doesn't do anything. It's always just going to give you the one measured bit that you measured. Yeah, so somebody says, if Alice sent only one qubit, how will we measure it 10 or 32 times? You couldn't, right? In a real experiment, you would need another way to deal with this issue of flaky measurements. So you're right. And that's why we're setting it to one shot here, is to be a little bit more realistic. You could not do this 32 times in a real execution of QKD. It wouldn't work, right? Because as you said, as soon as you measure it the first time, the qubit's collapsed. You can't measure it again. What if the result is also 50-50? I actually don't know what would happen there. There's a very low chance of that happening, though, because that would mean that 16 of your measurements would have to be wrong, right? And I think there's a very, very small chance of that happening. Okay, so with this function written, I am going to go ahead and run it. Okay, and then we're going to see what happens when we try this function out. So here we're going to use the simulator as our backend. So again, we do error.getBackend. Oh, I didn't mention this before. So this is the reason we have to have Q dot here is because of the way that we imported Qiskit, right? We said import Qiskit as Q. It's kind of the same as doing import NumPy as NP. It just assigns a shorter name to the library. So here, instead of typing out Qiskit all the time, we'll just do Q. And then it'll be Q.error.getBackend. We've seen that before. And then we're going to use the function we just wrote, this measure function. We're going to pass in Bob's bases. We're going to have this quantum channel, which is the encoded qubits that Alice sent him. And then we're going to simulate it. So let's see what happens. I'll go ahead and click run. Okay. And I guess let me also print out Bob's bit string just so we can see what that looks like. It'll be 500 bits long, so it'll be a bit large, but there we go. All right, so here is the results of all 500 of Bob's measurements. So in the first one, he measures a 1. In the second one, he measures a 0, and so on and so on, right? But as one of our students pointed out earlier, this is not necessarily the same as Alice's bit string, because Bob's basis choice was just random, not the same as Alice's. Okay, so let me just, I don't actually know where the option is to delete. There we go. Okay. All right, let's move on to step 6. Step 6 is another pretty easy one. After Alice has sent Bob her qubits, and crucially, after Bob has measured all of them, now Alice is going to say what her basis choices were. So Alice is going to announce to Bob, okay, first I encoded in the Z basis, then I encoded in X, then I encoded in X, then I encoded in Z, blah, 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 blah. Right? So essentially, she is sharing one of her random bit strings, but not the other one. Right? So remember, the Alice bit string variable, she hasn't shared that, and she won't. But instead, she's just going to share these basis measurements, or I guess the basis choice. Now, it's very important to highlight here that this occurs after Bob has done his measurement. So this has to be step 6. And you might think this is a little bit backwards, right? Like, why doesn't Alice tell Bob what her basis is so that Bob can just measure in the same basis? That's not how the algorithm works, is the short answer. This has to happen afterward. The longer answer is that this ordering here, doing the basis announcement after Bob's measurement, that's what guarantees secrecy. And I'm happy to talk a little bit more about that at the end, but you don't have to understand why right now. Okay, so pretty simple step though at the surface. Alice goes out and announces her basis choice. And step 7 is now the one that we've all been waiting for. How you take all of this randomness, all of this information, and put it together into some shared key. So for that, we're going to write one final function. I guess I should run this before I forget. We're going to write one final function called Bob compare bases. So Bob is going to look at whatever his basis choices were. So remember, he just flipped a coin a bunch of times, and whatever Alice's choices were. And remember, Alice also just generated a random bit string. So these are 2 random choices. Now Bob is going to check when they happen to agree, right? Because by chance, sometimes they pick the same basis. Also by chance, sometimes they pick different bases. So pretty simple for loop here. For each index, right, so 0 all the way up to 500, if their basis choice is agreed, then we're going to append I, which is just the index of the qubit, to this array called indices. And then we're going to return that. So this function just gives us the list of all indices where they happen to agree. So maybe they agreed on qubit 0, and they agreed on qubit 2 and qubit 3 and qubit 4 and qubit 6, right? So then this array that we return would be 0, 2, 3, 4, 6, and so on and so on. Okay, so let's go ahead and run this. And then I will run this as well. Okay. Now, final step is for Bob to send the agreeing basis back to Alice. So he's going to send back to Alice and say, hey, Alice, we agreed on qubits 0, 2, 3, 4, 6, and so on and so on. So now they both know where they agreed, right? They both know what their own basis choice was, and they both know where they agreed. So the final step for both of them is to construct the key. To do that, we're going to use this function here. So we start off with the bit string. So this, Alice's bit string is the one she originally constructed way back at the beginning. Bob's bit string is going to be his sequence of measurements, which we know was going to be partly incorrect, but some of them were going to be correct. Specifically, whenever they agreed on the basis, then their 2 bits should match. And so pretty much all we're doing here is we're starting off with a blank key. And now we go through every index that agreed, right? This indices is the agreed indices. And we tack on that bit from the string. And then we return our key. So note, if we had a 500 long bit string at the beginning, on average, our key is only going to be 250 bits long, because half of the bits in that original string, they won't agree on the basis measurement. Okay, so let's go ahead and run this. And now this is the final step. So we have, let's just go through step 7. Step 7 is pretty long, I guess. So Bob looks at all of Alice's bases, figures out which of them are the same, and then tells Alice, hey, we agreed on these bases. Now, both Alice and Bob are going to use those agreeing bases. So remember, Bob has put the agreeing bases in this classical channel. They use those to essentially prune down their 500 bits to the roughly 250 that happen to agree. So let's see if it worked. I'm going to go ahead and click run. Here we go. So Alice's key, 110, 1100, 111. That's just the first 10. And Bob's key also matches. So it worked. And that's the end of the protocol. So now, after all these steps have been done, Alice and Bob both know a 250-bit key that is secret, that is shared between them. All right, that was a lot. So let's go to questions. So I was kind of watching the questions as I was talking. So somebody asks, does the key change every time this code is run? How useful is this key? Right, so every time you do this protocol, you're going to get a new random secret shared key. That actually makes it quite helpful, because usually when you're doing symmetric encryption, you need a new key for every message you're sending. So every time you wanted to send a message, you would run this exact same code again, you would get a new key, and you would use that to send your message. Okay, so somebody asks, what if, however improbable, none of the bits matched? Yeah, so that can happen, right? Bob and Alice might flip their coins for their basis choices, and they might get exactly, opposite bases every single time. And in that case, when Bob looks for the agreeing bases, he will find that there are none, right? And so he'll say that. He'll say, hey, Alice, we had no agreeing bases. And so there would probably be some other protocol that says, if you don't have enough agreeing bases, just start again from the beginning and do it all over. And then you just keep doing that until you get enough agreed bases for you to construct your key. So somebody asks, why exactly 250? Let me clarify. It does not have to be exactly 250. It is random exactly how many bases will match. I'm just saying on average, it'll be about 250, but it could be more, it could be less. In fact, if we look here, just for curiosity, yeah, so here their keys are 254 long. Okay. So, yes. So people are starting to ask about eavesdropping. Well, actually, before I go into that, let me address this question. Somebody says, I don't understand how Bob's and Alice's keys will be equal after this process. So I think the simplest way to think about it is the following, right? Assume that Alice and Bob happen to agree on all of their basis choices, right? Then if we go to our encoding table, Alice is going to create all of these ket 0, ket plus, ket minus, ket 1 things. She'll send them all to Bob, and Bob is effectively going to figure out exactly what each of them was. Because he knows which basis to measure in, he's going to know with certainty which qubit Alice sent, right? And so he will then have the exact same result for her original bit string. He will know exactly what she used to create each of these encodings. Now, when parts of their bases don't match, that effectively means that some bits in that 500 long key are not necessarily valid, right? Because if Bob measured in the X basis when Alice sent him a ket 1, he's going to get randomness as the result, right? He's going to get 50-50, ket 0 or ket 1. It might be 1, so it might match Alice, but it might also not. And for this protocol, it's more important that we know with certainty the two keys match exactly than to try and sort of squeeze out as many bits as possible. So if the bases don't match, we just say, forget it. We're not going to count that bit. Move on to the next one. But for all of the ones where the basis does match, because of the way this table is constructed, Bob knows exactly what Alice has sent. Okay, hopefully that helps a little bit. All right, so shall we talk a little bit about eavesdropping? Because I think that is an interesting concept. So let's go back up to the summary of steps, wherever that was. Here we go. So I'll just do sort of a high level of where eavesdropping would occur, and I will do my best to explain why this protocol defends against eavesdropping. So the first two steps stay the same, right? These have nothing to do with communication, so they're just going to flip coins, generate their random bit strings. The third step, I guess, also stays the same. Okay. Now, eavesdropping can occur as soon as Alice and Bob try to send each other anything, right? So the first place that any sending happens is step 4. So this is where Alice sends Bob her qubits. Now, if you're an eavesdropper and you got a hold of those 500 qubits, what could you do with them? Well, first thing you might want to do is you might want to create a copy of them for yourselves, send the rest off to Bob, and then listen to the rest of the communication to figure out what to do on your qubits. But that doesn't work because of the no cloning theorem, right? You can't clone a quantum state. That's just a sort of fundamental rule, I guess, of quantum mechanics. And so that's not an option for the eavesdropper. Okay, next thing they could do is they could measure, right? They could essentially do what Bob does, pick a whole bunch of random bases, measure all of the qubits, write down the results, and then create the qubits back again, right? So if I chose to measure in the X basis and I got a 1, I would turn that into a ket minus, and I would send that off to Bob. So I would measure everything, I would create new qubits, and then I would send it off to Bob. Now, the issue here is that because I don't know, as the eavesdropper, I don't know which basis Alice created the qubits in, I might not be sending Bob the same set of qubits, right? If Alice created a ket minus and I flipped my coin and I got Z basis measurement, I might be sending Bob a ket 0 when Alice meant to send a ket minus. Now, that will be realized in one of the later steps. When we announce, or I guess, let me think for a minute where this would happen. Because yeah, the issue though is that, the qubits that are being sent off to Bob at that point would be different than what Alice originally meant to prepare. So I think I'm actually a little bit blanking on exactly how this is done. I think what they usually do is they will announce like the first part of their key to see if it matches. Because we know if this protocol happens exactly how we've described it here, the two keys will match with 100% probability. So I think what is usually done is once this whole protocol is finished, they will then go ahead and announce, okay, the first 10 bits I have are these. Is that the same as what you have? And if the answer is yes, they can be fairly sure that nobody sent Bob a different set of qubits, because the chance of the first parts of their keys matching with that different set of qubits is pretty low. So that's one possibility, right? The eavesdropper could intercept the qubits. And we see that that does not work. So what if they don't intercept the qubits, right? They let step 4 happen as usual, but now they're going to listen to everything else. They're going to listen to the classical communication. Well, let's see what they know in the classical communication. They know Alice's bases, right? So they know that Alice has encoded her message in some set of bases. And they know also which of those bases were agreed on. So maybe they know that, okay, both Alice and Bob measured in the Z basis for the first bit, and both Alice and Bob used the X basis for the third bit, and the X basis for the fourth bit, and the Z basis for the sixth bit. You know all of that, but you're crucially missing the information of what bit Alice actually encoded. You know she used the X basis for the sixth bit, but you have no idea and no way of knowing whether she used, well, whether she tried to encode a 1 or a 0. And so again, you're left with no information. Now that is a super high level overview of how that works. I'm not going to go into more detail on it now, just because it is pretty far outside. Well, it's related, but it would take a while to go through that rigorously. But yeah, you can basically think of it in that way. If I'm an eavesdropper and I can listen to any subset of these quantum channels, is there any way I could recover the original message? And the answer there should always be no. Okay, let me see. The qubits are... So let's see. Somebody says the qubits are different when measured, so how will Bob know if there's been any eavesdropping or not? Good question. So like I said, I believe, don't quote me on this, but I'm pretty sure the way this works is they will share as almost like a step 8. Actually, I think it, yeah, okay. So here they're saying we left out step 8 in this lab notebook. I believe what happens in step 8 is they both announce the first part of their keys, right? So they don't give away everything, but they say your key should start with 00110. And Bob will check his key. And if his key does not start with those same bits, then they know someone has tampered with the system. But if they do match, they can again be fairly confident that no tampering has happened. Cool. Okay, so somebody says, can teleportation help overcome eavesdropping in the 4th step? Yes. No. Good question. I'm trying to think if you could, because the thing is, teleportation still requires you to send 2 classical bits, right? And so if the eavesdropper could, listen in on these 2 classical bits, could they construct the teleported state? I don't actually know off the top of my head. I'd have to look into that more. Yes, you would have to share the entangled qubits in the past, exactly. I'm not sure if it actually deals with the eavesdropping problem, though. It might, but it also might not. Maybe actually I'll follow up on that. That sounds like kind of a cool problem. So I will throw that in my follow-up after the lecture, after the lab, sorry. Okay. So any other questions? I know there was one person who asked if I could go over one-time pad. So that'll be the final piece I do, but I promise it's actually quite simple. So it'll probably take me like 5 minutes to say how that works. Okay, so why don't I switch over to my tablet again, because I think that'll be the easiest way to explain this. Okay. Let's see if I can give myself a relatively blank slide. Maybe I'll just throw it at the end. Cool. Okay. Oh, this is weird. I don't know why it. Whoa. Whoa. Okay. That was weird. All right. So one-time pad. Now, like I said, the sort of the prerequisite for one-time pad, the preparation you have to do is that Alice and Bob both have some shared secret random key, right? Now, to illustrate one-time pad, well, actually, I can just do it with bits. Sure. So suppose that their shared secret key, I'll just keep it short, so that's a short example, is 1011, right? And suppose they want to communicate some message, and they want to keep it secret from an eavesdropper. Okay, let's say the message they want to send is 1010. And so again, the point here would be that we somehow want to get this message to Bob without the eavesdropper being able to figure out what it is. So the idea for a one-time pad is that you take the key and the message and you XOR them. So as a quick refresher on what XOR does, I'll just do a quick truth table here. So it goes 0, 0 becomes 0, 0, 1 becomes 1, 1, 0 becomes 1, 1, 1 becomes 0. So it's basically 0 if the two qubits are the same, or sorry, 0 if the two bits are the same, 1 if the two bits are different. That's what XOR does. So Alice is going to go and XOR everything. So 1 XOR 0 is 1, 1 XOR 1 is 0, 0 XOR 0 is 0, 1 XOR 1 is 0. And this is the encrypted message. So she's going to go and send this to Bob. Now, as a result of the way we've set this up, we pretty much just assume that the eavesdropper is going to know the encrypted message. Okay. Now, I'll first talk about what Bob does, just to prove that this works, and then we'll see if we can do anything as the eavesdropper. So once Bob gets this, he is going to do the exact same thing. He is going to XOR this message with his key. And you'll see that he's going to get the original message back. So 1 XOR 1 is 0, 0 XOR 1 is 1, 0 XOR 0 is 0, 0 XOR 1 is 1. And that right there is the original message that Alice was trying to send. So really simple, really straightforward, basically just 2 XORs. And of course, you could do this for a way longer message. You would just need a way longer key, right? But this, the reason this is supposed to be interesting is that the eavesdropper cannot do anything with this information. Well, let's think about it, right? The eavesdropper wants to figure out what this message was. Is there anything they can do with this 0001? The answer is not really, right? Like you'll notice that, for example, the first bit is different from the message, but the second bit is the same. The third bit is different and the fourth bit is different. There's no way for the eavesdropper to know that. There's no pattern. And so if the eavesdropper only knows this encrypted 0001, they have no idea and no way of knowing what that message could have been. It's equally likely that it was any 4-bit string, and the eavesdropper has no way of getting better information than that. Of course, that depends on this initial key being 100% secret. If the eavesdropper knows anything about the key, then they can start to make some guesses about what the message could have been. But with QKD, we know that that's impossible. It's guaranteed by the rules of quantum mechanics that the eavesdropper cannot know what's going on. So hopefully this should show you like, yes, the point of quantum cryptography is to send messages securely. Here's how you do it. But obviously this first step of establishing a shared key, that is by far, as you can tell, the more complicated part of this algorithm. But this is how the rest of it works, is you do these XORs, and that's how you send a message. Okay, so somebody says, this sounds interesting, but again, how can we transmit this in qubits? The measurements at Bob's end would change the qubits. So I think this is going back to just QKD, right? I don't think this question has anything to do with one-time pad. So transmitting information, like transmitting qubits, I guess, again, depends on the physical type of quantum computer, right? That's how you would physically transmit qubits. Maybe I'll expand a little bit on the step 8 that I sort of glanced over. So this is, I guess, separate from one-time pad. Maybe I'll just go to another slide. Did I forget to do the post lab? Anyway, whatever. I'm forgetting now. Okay, so let me try and address this question of, what happens if the eavesdropper takes all of the qubits that Alice sent, measures all of them, and then sends Bob another set of random qubits, right? What happens then? Well, because the qubits aren't the same, the keys that Alice and Bob, we did do post lab. Okay, good. The keys that Alice and Bob sent, they're going to be different, right? Because the qubits changed somewhat, these are going to be slightly different. So maybe this is the keys that they end up with, and Bob's looks kind of the same, but not really. If they just share, for example, the first 4 bits of their messages, they will immediately know something's wrong, right? Now, if everything went according to plan, if they had the same random strings, right? Alice has her string, and if Bob really did get the correct string, they can share the first part of it, and then they can use the last part as their actual key, right? Because once they've shared the first part, obviously that's not secret anymore. So they just use whatever's left over to do their actual secret communication. Okay, so somebody says, I was talking about the one-time pad. Is the communication classical or quantum? Oh, sorry, I see. The communication here is all classical. So the one-time pad is a totally classical algorithm. And in fact, you can do the one-time pad 100% classically. This step here called key establishment or key distribution, that is difficult to do classically, right? So basically what we're doing is we're using a quantum computer to do that first step, and then a classical computer can do the rest of it. And all of this is classical. Cool. Okay. Any other questions? I know we've gone quite long in this lab, but I think honestly, as we get to more and more interesting content, I am happy to go into more detail on some of it. So quantum mechanics is definitely not easy to fathom. Yeah, I agree. That's why it takes us like an hour and a half to describe this and about 5 minutes to describe the classical part of the algorithm. Honestly, that's how most things work in quantum computing. You'll learn the classical part and it's like, relatively easy. And then the quantum part takes you many, many weeks to wrap your head around. So I can certainly relate to that. Okay, if there's no other questions, I think I will wrap things up there. Thank you all so much for staying out right till the end. As always, this is recorded, so feel free to go back and watch if you need clarification on anything, or of course, post on Piazza. Have a great week, and I'll see you again in 7 days. Bye.